Yeah, so if you don't have it and you want to turn it in, or you want to pick it back up and turn it in later, you feel free. Anyway, so last time we spent some time talking about the chain rule. Chain rule is so easy when you learn it in calculus. I'm going to remind you again that chain rule is the assertion, but this is the calculus 1 chain rule. So with appropriate conditions, and don't worry, we will specify these when we get to the bigger picture here. With appropriate conditions on F and G, F composed with G of T is differentiable. And d by dt of F composed with G was equal to F prime of G times G prime of T. And I pointed out last time that we're covering up a whole lot of math when we do that, right? That we're sort of cheating when we use this prime notation, because there's more going on in the background. So why don't we look at like an actual complicated case that shows up once we start considering functions of multiple variables. So let's let x be a function. So x is going to be a function here, and it's going to be a vector value function. So x is going to take a domain T in R, and it's going to spit out a vector in R2. So you can think about x as being sort of a parametric function. It takes in a single value T, and it spits out a vector. And let's let f, and I suppose f will be scalar valued. F can be a function that takes a domain x in R2 into, say, I don't know, R fine. Nothing wrong with that. And let's suppose that this is differentiable at a point T naught in differentiable at T naught in T. And let's suppose that this is differentiable at a point X naught. So by saying X, how are there this many people in here? What is going on? There's somebody here with steel desks.
It's like
there's one here. There's one here. Is that okay? Here is a. Sit over here if you want. Sit over there if you want. Where do you want it? All right. Okay. I guess either they took a desk out or there's 36 people here. Oh yeah. Okay. So easy to get distracted here. Okay. So by this notation, we're gonna have to be a little bit careful what I mean here. When I say x as a vector naught, I mean in this case an x naught y naught. Okay, so I'll try to specify what I mean a vector or not. F is differentiable at a vector entry because its domain is a vector value domain. Okay. And then we have to make all these other assumptions too. T and x are open sets because differentiability doesn't make sense on the boundary of anything. If you need something to be differentiable, you stay away from the boundary. And let's make sure that the range of the function x is contained in the set x. That's the domain of f. So once you have all that crap set up, so what are we actually saying here? So there's this variable t over here that we're starting with, which is the independent variable. So we're going to construct a variable hierarchy. What does t do? T feeds into x. And x spits out a 2-variable output, right? Because x takes in this single value t, but it spits out sort of an x of t and a y of t. That's what it does because x takes a single variable in and produces 2 outputs. Okay, so just to make sure that we keep track of the notation here, this is x of t naught. So a t goes in, and x and y come out. That's what the action of x does. The function capital X takes that t and splits it up into 2 variables. Then each of those variables feeds back into f. So this is called the independent variable. These guys are called the intermediate variables. And in Colley's language, this is called the final variable or dependent variable, right? So that's not final. This is dependent. Backwards. This is dependent variable. Now, there's all kinds of induced partial derivatives all over this hierarchy. So I could take the derivative of x with respect to t, or I could take the derivative of y with respect to t. I could take the partial of f with respect to x, and I can take the partial of f with respect to y. Those are all changes that exist in this map, right? What this variable hierarchy is supposed to represent is changes in t induce changes in x and y, right? This is a meaningful thing to look at is how do the x and y change when the t move? Remember again here that this function x of t can be thought of as an x of t stuck together with a y of t, because it's taking in one and spitting out two. And as x and y change, we get changes in f. So if I want to, but the big picture is I don't care necessarily about what x and y are doing with response to t, or what f is doing with response to x and y. When I'm studying composition of functions, I want to know what f does as t changes. The idea that we have here is how can I take this hierarchy chart and turn it into an expression that looks like this. So given the hierarchy that we've got, what we want to do is we want to be able to write down an expression for this. What is df dt? So it turns out to be the case that to measure the total change in f with response to how it's changing in with respect to measure the total change in f with respect to change in t, I have to add together the change in f that's induced by going through x with the change in f that's induced by going through y, right? Both of these pathways both contribute to the change that f is experiencing. F is wiggling in response to both of these variables. So if I want to study its derivative, I have to account for both of these. As t changes, these both change. So it turns out to be the case that the way that you write this down, this is going to sort of give us the pattern that we're going to use to construct the large versions of this. Every pathway from the independent variable to the dependent variable contributes to the partial derivative with respect to that variable. So there's one pathway that runs through x. As t changes, x changes, and as x changes, f changes. So part of the change in f comes from this. That's part of it. That's the change in f that's induced by x moving in response to t. But also, f changes in response to y changing with respect to t. So once you start getting the idea of like these compositions, right? So these compositions where now we've got f composed with x and y for this function x, changes in the independent variable affect all of the intermediate variables as well. So we've got lots of pieces to keep track of. I don't know if I'm doing a good job of explaining this intuitively, why all these pieces are here, but f doesn't just move in response to t because f is not a function of t except by way of x and y. Okay, now the other thing I want you to imagine is it is pretty easy to see that this kind of notation is going to get ungainly pretty fast because I only have one independent variable and two intermediate variables here and one f. So there's not even a vector valued f happening. And already this is starting to look like if I put one more intermediate variable in here, I get an extra term. And if I put another independent variable here, I have a whole other equation with a whole bunch of other terms. So what we want to do is we want to try to write this in a notation that's going to let us generalize the chain rule to more variables. More variables here, more variables here, and more variables here. I want to study f's that are built out of vector valued functions in any compatible way, not just ones where we start with a real number and spit out a real number. There's just not very many functions that are interesting in this class. So before we do that, let's take an example. So let's suppose that f of x and y is
equal to x squared y plus y squared x. And let's suppose that x of t is equal to t squared cubed. I want to compute the partial derivative of f composed with x with respect to t. It's not really a partial, it's a full derivative, but that's what I want, right? I want to put this function inside that one and then compute the derivative with respect to t. So how do I do that? So I mean, again, this version of this is just reminding you guys how this works, right? Because I think they cover the chain rule in 241. If anybody remembers this, you've seen this before probably. So the sort of naive way to do this is just to plug it in, right? So one way to do it without using this expression at all would be to say, oh, well, f of x and y, which is x squared y plus y squared x, is just equal to, we'll plug in x and y, right? X is t squared and y is t cubed. X of t is t squared, y of t is t cubed, because remember, this all together we're referring to as x of t. And so this function is just f of t, f of x of t, y of t. It's just the function t squared times t cubed plus y squared t to the third squared times t squared. You can just plug in. This one's easy. Just plug in all the x's and y's and you end up with the expression t to the 7th plus t to the 8th. And so df dt is equal to 7t to the 6th plus 8 to the 7th, right? So there's always kind of a dumb way of doing this. Plug the thing in, do the composition, calculate the derivative. The idea is that plugging in starts to get remarkably inefficient when we get more variables. So the other way to do it would be like this. Df dx is equal to 2xy, and df dy is equal to 2yx. And dx dt is equal to 2t, and dy dt is equal to 3t squared. So having computed all these pieces, d of f composed with x should be equal to df dx times dx dt plus df dy times dy dt.
Like 2xy plus y squared.
What did I do wrong?
Df dx.
Df dx. Where did I do the split? Oh my God. These are just computed incorrectly. Thanks for pointing that out. Okay, I was just looking at that term. Okay, yeah. Sorry. I have lied to you. Df dx is 2xy plus y squared. And df dy is equal to x squared plus 2yx. There, is that better? Have I fixed the world of mathematics? And dx dt is 2t, and dy dt is 3t squared. It's usually easier to compute these things in individual pieces than it is to try to stick them all in compositions, because if you do the compositions by hand, you then have to use the one variable chain rule and get these boiling expressions where you induced all these compositions. Well, the efficiency in this comes from the fact that these chain rule type computations turn into multiplications at this level, instead of having to actually do this, where you plug everything in, and then you can imagine this is not typical, this sort of easy example I did here. So df dt decomposed with x, f should be this times this plus df dy, which was times dy dt. Oh no, I have variables that don't match. X's and Y's and T's. What do I do? I could. The cop out is to say where X is equal to T squared and Y is equal to T to the third. Because the point is, if you ever had that came from this, right? If you ever have to compute with this, the point is you don't ever have to plug these things in. If I gave you a specific number to compute with, you could just use the T value to calculate values of X and Y that you could plug in. So you can pull off the computation of the X and Y's without having to put them inside the function is the idea. So this is one acceptable answer to this. Does this make sense? The idea here is that you could keep going and you could plug in T squared and T cubed and T cubed and T squared and T cubed and T squared, and then simplify it all to get this back out again the other side, but you don't need to. Yep. So there's a subtlety there, right? I mean, the idea is that we use this notation when we're trying to emphasize. I mean, really what's going on in the background is there's some Z value that's responding, no matter how I name it, there's Z equals something, right? If we think about F as a function of T, I think of this object as F as a function of T, right? If I think about F as a function of X and Y, I actually think about it in this form. So when I'm using the composition symbol here, I'm trying to enforce the idea that I have taken this and I have plugged it into that, right? So that there is this explicit other function floating around that's been plugged into F, right? So because chain rules are about compositions, I mean, technically, no, there's not really any difference because they all represent the same variable, but this is emphasizing that this is a chain rule. This is a composition of an X, a vector valued X function with the F that's being evaluated on.
Like you were saying, if you were just putting X and Y, it would be
Yeah, exactly. So like this one right here, I would think of as being F of T. This I think of as being F of X and Y. Okay. So what we're trying to do is we're trying to build up, so build this idea up into like the full chain rule. So let's actually go one step more. Oh, actually, before I do that, let's look at the notation now. So there's a notational convenience. I mean, this is a vector analysis class, which means we're supposed to be writing stuff in vector language as much as possible. We want to stay away from, I mean, this is sort of the language of calculus. We have to resort to it when we're doing actual computations. But when we're writing these formulas down, if I wrote something like df composed with x dt is equal to df dx dx dt plus df dy y dt, I want to be able to write this as a product of vectors, either using matrices or a dot product of vectors. Ultimately, what I want running around in the background here is if I can use the gradient or the matrix derivative, I would really like to have this written as in that form. So if you pulled that apart as an inner product, what would it be an inner product of? Dot product. Like if you took this, I mean, to me, it looks like a dot product because it's a scalar, 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 scalar. These both involve F, these involve X and Y. So what two vectors could you write down that would make that dot product work? One of them is df dx, df dy, because there's a df dx in the first term and a df dy in the second. Remember, a dot product is first times first plus second times second, right? What is df dx multiplied by? Well, it's dx dt. So if this is a dot product, there should be a dx dt here. And there should be a dy dt right here. That is a gradient. Make sense? This thing is the derivative of the function x. So when we're doing these examples, when we're doing these sort of formulas, what we're always looking to do is to reduce these sort of, in practice, the reason I want you to imagine why we're doing this, why we're spending so much time talking about these sort of formalisms. Why are we spending so much time on notation? In actual practice, the functions that you deal with when you're modeling things like large systems of equations, or you're working on anything with physical applications, or you're working in applied math on fluid flow, you might have equations that have dozens of variables, dozens of independent variables, and dozens of intermediate variables, and dozens of response variables. So the systems you're modeling are very complicated. You don't want to have to write down some symbol that has ... lists all over the place, right? Like you want it to be compact in a way that you understand what the formula is doing. So what we're after here is a way of sort of packaging up an expression like this into something that uses objects that we're basically going to be computing anyway. The gradient is an object we will be computing here. So I want to be able to express this derivative in terms of that. There's an even better way to do this one, which is like this. So this is also a matrix product because it's the matrix df dx df dy times the matrix dx dt dy dt. This is how matrix multiplication works, right? The dot product of this row times this column. This, if you multiply it out as a matrix, it's this times this plus this times that. So this will turn out to be equal to df dx dx dt plus df dy dy dt. But these matrices both have names. This is df as a function of x times dx as a function of t. This is the matrix, the derivative of f as a function of x. And this is the matrix dx as a function of t. So that means we are definitely going to want to have the idea running around here that I can express these sort of, this one is not so bad. So I'm going to show you one that's a lot worse in a second here. That this type of expression is most efficiently coded as a product of matrices, where you have a derivative of the first thing times the derivative of the second. This doesn't look like that, right? This doesn't look like it doesn't look like a chain rule. It looks like a giant pile of things added together. But what should a chain rule be? Derivative of the first thing times the derivative of the second thing. This is the form that gives you the derivative that looks like a chain rule from calculus 1. Because calculus 1 says calculus 1 idea was that df dt was equal to df du du dt. That's the chain rule from calculus 1. It doesn't look like this. So the point of trying to rewrite this derivative in this matrix form is to get us the same sort of expression so that we can use it in the way that we chain rule in variable calculus. The conclusion of this is that the derivative of f composed with, oh, we'll leave the punchline out right now. Let's just write this. For now, what we've shown is this. df composed with x evaluated at t is the derivative matrix of f at x bar times the derivative matrix of x bar computed at t. And to me, that looks like a chain rule. That looks like this to me. Derivative of the first thing with the inside variable left alone times the derivative of the inside function. Okay. All right. Yep.
Why do you have an array box that X vector and not this?
What do you mean?
Like
here?
Yeah. Or no, it's very end.
Oh, I'm sorry. You are absolutely correct. I'm not, that there's no inconsistency. I just meant f evaluated at x. Really what I'm saying here is in our case, it would be x comma y either way, right? Yep.
Why does the derivative the X vector become
Why is it stacked up like this?
Yeah.
So forget this for a second. The reason it's stacked up like this is just on the level of that's the matrix multiplication that gets you the formula. That's the first thing, right? It's just like if I arrange the matrix multiplication in that way, I get out the formula that I was after. Now, why is this equal to this derivative? So when we define the derivative, remember that what we did was we said, okay, if I had some function f, and suppose that f was a function of x and y, but f spit out something like this. It had two components. So f of x and y was a vector output like this. I'm driving towards why the derivative is defined this way, right? What we decided, or what we talked about, we defined the derivative of the vector function f is supposed to be df1 dx, df2 dx. So derivatives in the same variable go down as columns, and derivatives of the same function go across as rows. So the derivative of the function in the first row, its partial derivatives are rows. df dx, df1 dy in the first row, df2 dx, df2 dy in the second row. So derivative matrices always have the same variable in columns and the same function output on rows. This thing has x here is a vector output. It has two components, an x1 and an x2, or an x and a y output, right? So each piece is going to get its own row, but there's only one variable. So the matrix only has one column. The idea here is if you did the same picture, but I tell you that x of t is equal to x of t, y of t, then the derivative of x, well, this only has one variable. So dx is going to be equal to what are all the partial derivatives of that row? Well, it's just dx dt. There's nothing else to take a partial derivative with respect to. Then I shift down to the second slot and say, okay, now I'm going to put in all the partial derivatives of y down below it, which are dy dt. So in derivative matrices, the same function outputs, the same element of the vector stays in the same row, and the variables all stay in the same columns. So that's why here too, this thing is the same function with different variables, so it gets stacked up as a row. This is the same two different functions with the same variable, so it gets stacked up as a column. All right. Okay. So let's do a slightly more complicated example here, which I think will illustrate the technique that I'm after. Okay, suppose that we have this picture. Let's make this more complicated so we can see how this generalizes. I'm going to give you a picture that looks like this. I've got an f. F is fed into by three variables, x, y, and z. And then there's independent variables s and t. So there's a lot of pieces to computing the partial derivatives of f here. So suppose that I want to know what the derivative of f composed with, let's be careful here. Let's let the function x be equal to x of s and t, y of s and t, t of s and t. Does that make sense? We're just saying whatever this middle variable is, it's a vector value function x that takes in an s and t and spits out an x, y, and z. All right? And function notation here. So we're going to build this picture, then we're going to compute an example. What is df composed with x of s? And the answer is every pathway that gets you from s to f contributes to the change in f. If you're going to compute this partial derivative, you have to keep track of every single thing that s changes. And every one of these lines represents a partial derivative. So hopefully you'll believe me, instead of belaboring this, if I write down that what this picture would tell you is that the partial of this composition with respect to x should be df dx, dx ds, plus df dy, y ds, plus df dz, dc ds. df dx, dx ds, df dy, dy ds, df dz, dz ds. Those are all the things that moving s changes that affect f changes. All right? But also, there's more derivatives of this. there's the t derivative. So you can already tell, like, I'm tired of writing these on the board now because this is taking a long time to write all this stuff down. I don't care about trying to categorize every single possible case of how this stuff goes. I'm already starting to think at this moment, it would be really nice if I could write a single object down that encodes all this information. There's a lot of information here. 2 different partial derivatives of f of this composition with respect to 2 independent variables, each one of which has 3 pieces. So we're doing it the nasty way, and then we're going to come back with the notation. The reason, again, we have to like emphasize the notation here is because the matrix derivative approach is going to underlie the applications we're going to have here when we start actually using this stuff to study physical problems. So the first observation I'm going to make is this looks an awful lot like this to me. It looks like I've taken a matrix that looks like df dx. But I've taken something like df dx, df dy, df dz. That has a df dx, df dy, df dz. This has a df dx, df dy, and df dz in it. So it looks like I've taken a row matrix like this, and I've multiplied it by some blob. Well, what would I have to multiply it by to make this happen? What has to go in this column in order for this equation to fall out?
df dx.
All right, not df ds, dx ds, dy ds, dz ds. Why did I keep all of these in the same column? Independent variable, and also the matrix multiplication of this row and this column give you this output. This output corresponds to this row times this column. Where's the other equation going to come from? The next column, which should be dx dt, dy dt, dz dt. This is df evaluated on x times dx evaluated on st. You could call it, the book likes to call this t vector as well, right? So you can think of t as being ts, sorry, st. And then this would be in that form. Now we almost have a really elegant looking equation here, except I've got, how am I going to glue all this together? This matrix times this one gets you this as one row, and this is a second row. If you multiply those out, what you get is this in the first row and that in the second row. But we want these to be equal to this guy. Yes. Okay, now what's the next thing I need to do here? What else needs to be here to make this happen? I mean, this has to be somewhere too, right? This matrix was 1 by 3. This matrix was 3 by 2. The resulting matrix should be 1 by 2, right? So does that mean I'm going to write a row or a column here? 1 by 2 matrix is 1 by 2 is a row matrix, right? 1 row, 2 columns. What goes here? Perhaps unsurprisingly, dt goes here. Now, does that make sense? Does this meet our convention? Do we have different independent variables in different columns? The answer is yes. This is df composed with x of s and t. Or if you like, d of f composed with x, t is a vector. So all of this computation has just given us a formula that says that if I want to compute the derivative of a composition, I mean, that is about as close to a one variable chain rule as you're going to get. The derivative of a composition is equal to the derivative of the function with the inside variable left alone times the derivative of the inside function. This is the chain rule. And this actually works. This is the general form of the chain rule. This works for any f, any x, and any t. So any number of input and output variables, this expression works. This is an amazingly compact way of writing these derivatives. So this is the chain rule for any matrix size input or any vector type input and any vector type output. This is the form, the general chain rule. And the idea is you want to work this way because you don't really want to start plugging functions into themselves when there's like millions of input variables and millions of intermediate variables. So let me do a quick example here. I wrote up earlier. I'm going to show you how this stuff works when you do it. And then I'm going to give you like the first sort of interesting application of these ideas. So again, keep in mind that when you do these derivative matrices, the derivative matrix has rows stay rows and independent variables are arranged in the column. Okay, each independent variable is going to get its own column. All right, so here we go. Let's define f of x and y as a vector function to be equal to x minus 2y plus 7, comma 3xy squared, and g, say, of RST be equal to r plus 2s r squared st. These are polynomial functions, and so their domains are everywhere, so there's nothing inconsistent about composing these with each other. The domains are all fine. So I say, find the derivative of f composed with g as a function of r, s, and t. Now, the long-winded way to do this would be to start plugging these things in all over the place. Plug them in for x, plug them in for y, multiply everything out, take partial derivatives. What I want to do is I want to do this using the chain rule formula. So if I want to compute this derivative where I've composed these, I need to compute the derivative of f and then multiply it by the derivative of g. This should be equal to the derivative of f on its original variable here. Notice that I am treating g like it is the variable xy. So even though this notation is a mismatch, the idea here is I'm evaluating f on g, thinking about g as spitting out x's and y's. I'm going to I'm sorry, use the brackets again. My bad. And then I'm going to multiply that by the derivative of g with respect to r, s, and t. If you like, you don't need to put the g here. You can just do this. It's less confusing to leave it that way. The derivative of f in its original variables times the derivative of g, which are the variables that are going to be fed into f. So, more derivative practice. What is this? What goes in the corner here? df1 dx. What is df1 dx? There's df1 means the first slot of f. I can write it down. df1 dx, df1 dy, because the same function gets the same row, but the variables get different columns. Then df2 dx, df2 dy, times the derivative of this thing. Okay, what size matrix is that going to be? Well, there's going to be 2 rows, but there's 3 variables, so there'll be 3 columns. dg1 dr, dg1 ds, dg1 dt, dg2 dr, dg2 ds, dg2 dt. This doesn't need to be written out when you're working with these exercises. I'm just trying to emphasize the connection between the formulas that we're writing and the computations that we're going to do. So the derivative I'm after should be, so what is that? df1 dx is 1. df1 dy is -2. df2 dx is 3y squared, and df2 dy is 6xy. The derivative of the g function just means take 3 derivatives of this with respect to the different variables. dg/r is 1, dg/ds is 2, dg/dt 0. For this entry, I do the r derivative, the s derivative, the t derivative, and I'm going to get 2r st, r squared t, and r squared s, I believe. And then you quit. You're done. You did it. You calculated the derivative. If you had to work with it, now suppose somebody comes along and says, oh, well, that's not good enough. That you just told me what df composed with g was at r, s, and t, fine, but I want to know what happens at r, s, and t is equal to 1, 1, 1. Now evaluate that derivative at a point. Well, r, s, and t are easy to find. Where am I going to get the x and the y that I need for their derivative? If only I knew a definition of what x and y happen to be. Well, you can just evaluate g at those points, right? G of r of 1, 1, 1 is equal to 3 times 3, 1. If I take g and evaluate 1, 1, I get this. This is the x and the y value that you plug into that matrix. That's why you don't have to plug in and make the composition. The values that g spits out are going to become the inputs for f. The values that g, remember, what we got here is we have an r, s, and t that feed into an x and a y that feed into, sorry, the function f. So if you get a specific point, you can just compute the x and the y values. You don't ever need to compose anything. The function basically lives completely separated out. So what you get here would be 1 minus 2, 5, 3, 6 times 3 times 1 is 18. And then 1, 2, 0, 2, 1, 1. And then if you're extra lazy, you just leave it as a multiplication of matrices and don't touch it again. Put it in Mathematica at this point, yeah. I mean, really, not even Mathematica. The point of this is not that you're going to be hand computing these things. The point of this is this structure of pulling these functions apart into these derivatives is the theoretical approach for how these problems are built when you're working in practice. So yeah, in the same way that nobody ever sits around and computes a derivative of x squared, right? This doesn't happen. Or like, when's the last time you integrated an inverse trig substitution? It wasn't specifically set up to test if you remember how to do it. In fact, actually, how many people even here remember how to do an inverse trig substitution? Right? The point is not that you'll be doing this. It's that you have to work with objects that look like this. And so it's important to be able to interpret where they come from and the fact that these do, in some sense, still represent slopes. I know it's hard to think about the slope because a matrix comes out, but it still generates a linear approximation for that function that you started with. Yep. So remember that at the bottom, when we start talking about tangent approximations to functions, we talked about tangent planes, but the idea is that you can write down in terms of a matrix derivative, you can write down an approximation for a function in terms of this. This is sort of like the slope of a linear approximation. I mean, it's a hyperplane, but it's the same idea. You imagine that this function is some twisting surface that we can't possibly imagine in like R10, 10-dimensional space, right? And your computer says, I have no idea how to work with this 10-dimensional manifold that you fed me, right? Like it sucks. I have to do it all numerically. Like everything curves all over the place. It's going to take 1,000,000 hours of computer time to reconstruct it. So you approximate using this matrix, and instead you just, as long as you don't go far away from whatever your starting point is, the plane that this gives you is almost the same as the function that you're starting with. No, so f here, these two things together make the function. What we're saying is if I give you a function in two pieces, that the combined function, a lot of the most useful functions are built out of two parts or more parts that are stuck into each other, right? So if you've got them in parts, this says work with them individually, with the idea being that you could build a line or plane that approximates the function. This is impossible to understand. You can't draw it, you can't visualize it, it's hard to compute. But if at any point you can replace it with something flat, matrix multiplication computers do fast, right? So when you're working with these functions, I mean, so like almost no function is capable of being visualized in any system you've ever written down, ever. No problem in physics, no problem in engineering, no problem in higher math, ever turns into a function you can visualize, solve, or understand, ever. So you have to come up with a way of working with these things that can be computed. And the way that computers do this, and the sort of math that you use vector analysis for, is it takes problems that are highly nonlinear and turns them into linear functions, which are great as long as you keep small around your approximating points, right? So locally, who cares if this thing is some horrendous thing twisting through 10-dimensional space? It's just flat. Flat things are easy to compute, they're easy to work with, they're easy to understand. So we don't ever work with those, we work with these. And basically every method in applied mathematics, I wouldn't say every, but every linear method in applied mathematics basically boils down to taking complicated expressions like this and replacing them with matrix computations. Yep. Oh, Taylor polynomials are coming for sure. Taylor polynomials in several variables are awesome, and that's the single most important idea of undergraduate calculus, and it gets basically not anywhere near enough attention. And it's most important because we can do it in any number of variables. And absolutely, we're going to use these ideas to build Taylor polynomials. And these matrices turn out, and you can imagine, if you have Taylor polynomials in 10 input variables, well, you're going to have, even just in 3 variables, right? What a Taylor polynomial look like? Well, there's going to be x's, and y's, and z's, and xy's, and xz's, and yz's, and xyz's, and x squared y's, and x squared z's, like this boiling pile of terms we've got to deal with. And so the vector notation is going to make that much easier to do. So yes, Taylor approximation is absolutely a menu. Yep.
So when you multiply out 2 by 3, is the resulting matrix then just like the first row is just F1 with respect to each of them?
Yep. Absolutely. Yep. So basically what you're doing is when you actually multiply this out, you get a matrix where the first row is sort of the flattening. It's the linear approximation of row 1. And then you get a line that approximates row 2, right? So there's a plane in row 1 and a plane in row 2, basically. So you're just putting planes everywhere. Remember, the secret of calculus is everything is a line. And that's all, that's literally all we're doing here is saying like, yeah, who cares? It's just a matrix multiplication. That's linear. All right. If you want an example of this, you might look at the end of this section. Polly goes through the example of showing you that the thing you've done already probably in the past, every time you've used polar variables, every single time in your life you've written this down, and most of you have done this a lot, this is, if you ever took a function and made this substitution, you've actually done a composition of a function where you started with a function f in x and y, and you composed it with a function of r and theta. And there's a way of keeping track of the relationship between the x and y derivatives of the function and the r and theta derivatives that come from it. So this type of polar change of coordinates is exactly the sort of thing that we're studying here. I'll run through the example of how this works next time. But this is a super important one. And also, those you poor guys that have to deal with spherical and cylindrical coordinates, it also can be used to represent those as well. The core ideas in physics. All right, see you guys next time.